ICPS conference. Is everybody ready for Days of Science from Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of the science. Is everybody excited for this conference hosted by Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS. Welcome you all to our ICPS conference. Is everybody ready for Days of Science from Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of the science. Is everybody excited for this conference hosted by Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS.
We are going to wait just one more minute.
Welcome you all to our ICPS conference. Is everybody ready for Days of Science from Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. It's time to share your great knowledge of the science. Is everybody excited for this conference hosted by Mexico? Mexico now. Let's get to science talks right away. It will be awesome time every day. Everyone around the world can have their say. It's ICPS. ICPS.
So, hello everyone again. My name is Melissa and I am the Scientific Program Coordinator of the International Conference of Students, Puebla 2022. It's a great pleasure for me to introduce our next guest speaker, who is going to give us a talk about hunting for dark matter deep underground. In 2009, Dr. Eric Vázquez obtained a recognized postdoctoral position at the SNOLAB laboratory in Sudbury, Canada, where he was appointed as researcher in 2014. Since 2015, he's a researcher in the UNAM Institute of Physics and adjunct professor at the Laurentian University of Canada. His research focuses on the properties of neutrinos and the search for dark matter by direct detection inside of the SNOLAB underground laboratory in Canada, 2 kilometers below the surface. Dr. Vázquez is also the leader and founder of the DM, Dark Matter Neutrinos Laboratory for instrumentation and detectors of neutrinos and dark matter. He participates in various committees in SNOLAB and in the development of an underground research laboratory in the state of Hidalgo near Mineral El Chico. Without further ado, please join me in welcoming Dr. Eric Vázquez.
Thank you, Melissa. Thank you for the invitation, and thank you for the introduction, for the very nice introduction. So let me share my screen. Oh, I need to share sound also because I have a video at some point in my presentation. These are my slides. I think that you should see them right now, right? Okay, so I'm going to talk a little bit about one of my main research topics here at UNAM in Mexico. This is connected to experiments in the deep underground laboratory Snow Lab in Canada. Erica Caden talked about the laboratory yesterday. So I'm going to focus now on the search for dark matter through direct detection. And then I'm going to explain a couple of experiments as examples on how we do these searches. This is the outline of my talk. First, I will briefly give an introduction about dark matter and mainly about, mostly about direct detection. And then I want to show you two examples, Deep 3600 and PICO, two experiments, leading experiments. And probably I will not have time to talk about a third project, a combination of the technologies between Deep and PICO. But I hope that I will quickly show you the idea behind these experiments. Okay, so first I'd like to talk about dark matter direct detection. Well, dark matter, we know that there is about 85% of the matter in the universe that we don't know. Basically, it is 95% of the matter and energy content in the universe. And here you can see the pie chart of the universe, where we have this standard model of particle physics that we know it accounts for roughly 5%. And then we have two components, dark energy, which is roughly 69–70% of the contents of the universe, and then dark matter, which is 26% more or less. And this is basically our universe today. And this is based on an impressive number of observations at different scales. And my main research topic in this talk will be dark matter. There are people trying to solve what dark energy could be, but that's outside of the scope of this talk. And of course, many people doing research in the standard model. So this is physics beyond the standard model. So this is one slide that I like to show when I talk about dark matter. Basically, the evidence that we have is impressive, and it is in different ranges. So on the left, we have the typical rotation curves of galaxies. This comes from Newtonian dynamics, basically the gravitational force. And what we should see when we try to describe the motion of the galaxies and the stars, basically should be with a function that it decays, that it is basically proportional the velocity to 1 over the square root of r. But the actual observations, basically what we have is that the velocity starts to increase and then it becomes flat, as you see here in some examples. So this was one of the first evidences for dark matter. And one way to solve this is basically by adding a halo of matter that surrounds the nearly flat galaxies that we have. So basically, this is the first evidence that we had, one of the first evidences that we had for dark matter, and it comes from earlier than Zwicky, but it's typically, we start with Zwicky discussing about his proposal when he measured the velocity distribution of the coma cluster, and of course, all the work of Vera Rubin by measuring many velocity distributions of galaxies. And then there is another evidence that this is through X-rays. Basically, we can measure the temperature and distribution of the gas, and then from that we can get the average speed of the molecules, and then from that we can obtain the mass. And with that we extract the amount of matter that it is present there. And there is some missing matter there, giving a higher velocity, average velocity of the gas in the molecules. And then third is the gravitational lensing, the weak and strong lensing actually. And basically with this, what we do is by observing the bending of the light that we observe for some galaxies and clusters, we can deduce the amount of matter that it is between that galaxy and us. And it happens that this is different for the visible matter. We have an excess, an amount of matter missing there that we cannot we cannot see basically. And then on the right we have some other evidence at different scales. First, we have the cosmic microwave background, where we basically measure the distribution of the photons in the sky, these very low energy photons, and we measure its energy, its temperature as function of the angle, and with that we obtain a distribution, and we can fit to our standard model of cosmology, the lambda CDM model, and in that we account for some fraction of baryonic matter and some other fraction of dark matter, some fraction of dark energy, and with that it happens that everything fits when the content of dark matter is roughly the 26% that I mentioned, and the content of dark energy, it's about roughly 69%, and there are satellites who have been measuring this for years, and we have a very precise comparison between the data and the model, and everything fits with this description of the universe where we have these components of dark baryonic matter, and dark energy. Then we enter what we call on the precision cosmology. We can estimate, we can calculate the abundance of primordial elements, and we combine these with predictions from nucleosynthesis. And then we get what fraction corresponds of the baryonic matter to the contents of the universe. And I also talk about dark energy and how we can measure this with supernovae, for example. But all this fits in this global framework that fits within the lambda CDM model. And then for structure for formation, we have simulations of the universe at large scale, and we can compare that with what we see, and the same with this fraction, this pi that I showed here. Everything fits in this coherent framework. So the question is, what is this missing component? What is the dark matter? So first, let me talk about a little bit about what we could rule out. We basically have eliminated any explanation within the standard model. We need physics beyond the standard model. It cannot be baryons, because we can calculate the baryon fraction through the CMB and nucleosynthesis, as I just mentioned in my previous slide. We can also look for clusters of baryons, non-interacting. And basically, there is a large range where we have eliminated this possibility, this large mass range for these objects. We can also talk about, why not, about Mont or Teves. That's basically modify gravity, modify the dynamics, even at a relativistic level. But the thing is that we just need to get the entire range of observations right, not just the galactic rotation curves and clusters, which is what these models mainly solves. And basically, if we assume that this missing component is a particle dark matter, well, it is easy to explain everything, and we can prove it. It is testable. And this is basically the main hypothesis behind this, that we assume that these dark matter are particles based on this evidence that I just showed, and also what we have ruled out. So when we talk about the properties of dark matter, well, we know that it interacts gravitationally. That's how we have measured it. We know that it is stable or long-lived, the age of the universe and above. It cannot be relativistic, because then we wouldn't see the current structure of the universe. There is no way that it can be baryonic. So basically, we have ruled out everything within this standard model of particle physics. It needs to be electrically neutral. And basically, it has to interact very, very, very feebly. And here, there's a very nice diagram of all the possibilities that dark matter could be. And there are people working even in these extensions of the Newtonian dynamics, or searching for particles with different masses, different ranges. And here you can see a plot of basically the mass of the particle. And you can see that there are candidates with masses of micro electron volts, milli electron volts, which is 10 to the negative 3, 10 to the negative 6, even smaller. And then there are particles above GeV, TeV, that basically could be candidates for dark matter. Of course, if the mass is small, then there are more particles. If the mass is higher, there are less particles, just to account for the current density that we observe in the universe. And my research topic is in this area, in this green area, which are WIMPs. We have expanded actually in our experiments for particles below and above these mass ranges. But basically, I'm going to start talking about how we search for dark matter in these mass range particles of a few GeV, less than 1 GeV, half GeV, up to TeV. So, this is basically comes to search for WIMPs. This is now, this has been for many years, for 30 years, the most discussed candidate. It is what we call the weakly interacting emassive particle. These particles were basically produced during the Big Bang. They were produced in thermal equilibrium. There are many theories about how they could be produced, but first, the simplest is that basically they were produced in thermal equilibrium in the energy universe. And then basically, as the universe expands and cools down, then these particles decouple. And that the basic idea is that they don't have enough energy, and since the universe is larger, they rarely find each other to annihilate. And then it comes to get a cool down, a freeze of these particles. And in principle, they are still around today with densities of about a few per liter, considering this GeV range mass. And of course, there are many theoretical ideas. They were motivated by SUSY models, but that's not the only main theoretical aspects behind this. As a matter of fact, we don't know how the coupling could be with this dark sector and the standard model. And it doesn't have to be only one particle. As far as we know, the standard model of particle physics is very rich. So we could expect that this dark matter, sector is this dark sector is also very rich in particles. So how do we search for these particles? Well, there are three ways in which we can try to detect them. One is through direct detection. That's the topic that I will discuss in this talk, where basically we have material atoms of certain isotope, and then we expect that these particles hit one of these atoms, and then we measure their recoiling nucleus. That's how we would look for these particles through what we call direct detection. There are also two other ways that I will not discuss in this talk. One is indirect detection. Indirect is basically by searching by the signature that these dark matter particles leave when they decay or they annihilate in areas, in regions of the universe where there is a high density. This would be in the center of our galaxy, where the density is very high, and we would expect that these particles annihilate, and we can measure the products if they annihilate to particles of the standard model, like photons of neutrinos. And then we can produce them in colliders, and they basically would be observed through a missing mass when we reconstruct the events in a collider, for example. So, but for now, I'm going to talk about direct detection. So basically, this is a cartoon of what we are looking for. You can see here a series of atoms. This is a material. And then we expect that the dark matter particle comes, hits the nucleus, the dark matter particle goes away. And then this nucleus deposits some amount of energy. This amount of energy is in the range of a few keV. It moves a few nanometers. So that's what we need to measure. For that, of course, we need to assume, to calculate the rate, assume interactions, how is the interaction, and how is the dark matter distributed. And historically, experimentalists have searched two interactions. One is that we call spin independent. And in this case, we assume that the coupling goes to all nucleons. And there is a second one, which is the spin dependent, in which we assume that the coupling goes to the spin of the nucleus. And of course, this is favored to isotopes that have one unpaired nucleon. And this is basically how we can calculate the typical cross sections, where we have the number of protons and the neutrons and some structure functions. And also this is for the spin independent, and for the spin dependent, it basically comes to the spin of the nucleus. And this is basically what it goes into our calculations. So basically we have certain amount of material, kilograms, tons. Currently experiments are in the range of a few tons. And then we wait for some time, a year, 2 years, and try to identify those nuclear recoils. And with that, we can, if we observe events, we can estimate some rate, number of events, or if we don't see, if this is zero, if we don't see any events, then we can exclude some region. So what goes into this equation? Well, in this equation, we have four main components. One is the dark matter density component. This comes from local and galactic observations. There is an uncertainty, historically within a factor of 2, roughly. And basically here we have estimates for the density, but we don't know the mass of the dark matter particle. Second, it comes the particle physics component, the unknown, that comes from the cross-section. Basically, this cross-section is related to the coupling, to the interaction. As I said, it could be any theory could be possible. Historically, we search for these two, spin independent and spin dependent, that go into this equation. But there are many other models, and this scales with the number of nucleons in the atom, in the isotope that we use. Then it comes the nuclear part. The yellow is the nuclear part, that it is basically the shape of the nucleus, right? How the dark matter particle sees the nucleus. And for that, we have also different models. This is a non-relativistic interaction because these particles move with a velocity of 500 kilometers per second, more or less. So basically, we know how to calculate this. This is very well known. And finally, we have to assume a distribution of the dark matter particles. So basically, if we assume we are this idea that there is a halo of dark matter around the galaxy. So basically, we have to assume a certain velocity distribution, typically a Maxwell-Boltzmann. That's what we assume here. This comes from also measurements. And of course, there could be variations and there is some uncertainty, but basically we also can assume how the velocity of the dark matter particles is in the Milky Way. Then when we compute all these, there are two unknowns here. One is the mass of the dark matter particle, and the other is the cross-section. We don't know what type of interaction, and we don't know what mass. But of course, we can test our models against measurements in a two-space parameter plane, which would be this. Here we have this cross-section versus the WIMP, the dark matter particle mass, basically this one and this one, these two. And if we don't observe events, we can exclude some space in this plane. And basically what you can see here in red are the rule out regions. Basically, these are values that have been excluded by current experiments. This is from a few years old. Probably we are a little bit below this, near this corner in this yellow area. Here in yellow, we have the coherent neutrino scattering fog, or FLOR as used to be called. Basically, when neutrinos mostly in this area, solar neutrinos, will produce the same nuclear recoils as dark matter, and this will be an irreducible background. And then there are two models that just to give you an idea, these are the generic WIMPs that I just discussed, produced thermally during the Big Bang. These are possibilities, the area where they could be. And then here are other theoretical models, feasible theoretical models, one called asymmetric dark matter that basically is a comparison between baryonic matter and dark matter. And this is the range or the area where this asymmetric dark matter could be. And of course, there are many models that are in different places in this plane. And of course, it could extend below this 1 GeV or above this 10 TeV mass. But the experiments that I will describe are mostly sensitive to this mass range. And this is the current state with cross sections of 10 to the negative 45, 44. That's basically the limits that current detectors have placed. And of course, this comes from measurements. This red area has been ruled out, as I mentioned, by experiments. So how is the experimental or the basic experiment that we could do? Basically, we have a chunk of matter. It could be any atom, xenon, argon, fluorine, germanium, and we place them at some place, and we expect that the dark matter particle would come and hit one of the atoms, and then there will be this recoil. That's what we want to measure. And as I mentioned, we have some assumptions. We live in this dark matter halo with a local density of about 0.3 GeV per cubic centimeter. That's what we have measured at different scales, with a velocity of roughly a few hundreds of kilometers per second. And then we look for the coherent elastic scattering. But we have one problem. We are surrounded by many backgrounds from natural radioactivity. These are neutrons, muons, gammas, beta decays, alpha decays, even neutrinos. So basically, if we have our detector placed here on surface, so we have backgrounds that go up to 10 to the 11, 10 to the 12 events per ton per year. So basically, in 1 ton of material in 1 year, we would see 10 to the 11, 10 to the 12 of these interactions. And we are searching for one candidate for dark matter, one interaction for dark matter, less than one with the current size of the detectors. So we need to eliminate, reduce, or discriminate all these backgrounds. And for that, we do 3 things. One is we go underground, because by going underground, we use the air as a filter to reduce, to eliminate the majority of the cosmic rays. And then we also shield our detectors to avoid environmental radiation reaching our detectors. And then we do a careful selection of the materials so that they don't have traces of radioactive materials that basically will produce the same interaction as dark matter. So the goal here is to reach less than 1 event per ton per year. Here on surface, we would have 10 to the 11, 10 to the 12, but here we would have less than 1 event per ton per year. So basically you have 1 ton of material for 1 year, and there will be known less than 1 nuclear recoils in that material. Why? Because there will be not the cosmic rays. It will be shielded from the environmental radiation, and the materials will be pure. Radioactively speaking, they will be pure. With this, let me explain what it would be the receipt for the detection, the direct detection of dark matter. Basically, we need to detect these tiny energy deposits. As I mentioned, they are a few kV, and here's just a simple calculation. It is non-relativistic. So I assume a mass of 100 GeV with a velocity of 100 to 100 kilometers per second, and that gives 50 kV. I need to be able to measure 50 kV energy range of nuclear recoils. And then we also need to suppress the background. For this, as I mentioned, there are 3 things that we do. deep sites to reduce the cosmic ray flux, shielding, and a careful choice and selection of the materials. And then finally, because we still cannot reach the 10 to the 11, 10 to the 12 elimination of those backgrounds, we need to do some background discrimination. And this is because in this cartoon that I showed you, the WIMPs, the dark matter, will hit the nucleus. But there are particles like gamma rays, electrons, that they will most likely interact with the electrons, the electron cloud surrounding the nucleus. So those will produce electron recoils, not nuclear recoils. But those electron recoils that you can see here in this cartoon, they deposit also energies of a few keV. So we are not able to differentiate just by the energy if it was a nuclear recoil of an electron recoil. But you can see that the topology is different. There should be something different, because in one, the nucleus is recoiling and the other is the electron. So if the energy is the same in the similar range, it's kinematics, of course, there should be another way. And we can discriminate the nuclear recoils from the electron recoils with some parameter that I will show you in an example when I explain a few of the experiments. So this discrimination basically allows to separate the electron recoils from the nuclear recoils, because we know that the dark matter candidates will be with the nuclear recoils because of the mass range in which we are searching, which is a few GeV up to TeV. Okay, and then of course we need a large target mass, just basically to scale our detectors so that we are more sensitive to lower cross sections. And first, I'd like to talk about these three background suppressions. I'm going to talk about deep sites to reduce the cosmic ray flux. For that, basically, we build our experiments deep underground. There are roughly 12, 15 laboratories where we can install these detectors. One of them is SNOWLAB. You heard about SNOWLAB yesterday when Erica presented. This is the deepest and cleanest large space international facility in the world. It's roughly 2 kilometers below the surface in a nickel mine. In Canada, they usually compare it with the CN Tower, which is 200 meters, so it's 10 CN Towers, more or less. In Mexico, we have the Latin America Tower, Latino Tower, and that's 100 meters, so it will be like 20 Latino towers. So if at some point you come to Mexico, just look at that tower, or if you go to Canada, look at the CN Tower, and just think about 10 or 20, and that's how deep we are, of course, in the opposite direction, right, underground. And then roughly 1.5 kilometers, it's located, SNOWLAB. It is a facility with different tunnels. This is where the SNOW experiment is located. The SNOW experiment received the 2015 Nobel Prize in Physics for the discovery of neutrino oscillations. That's where SNOWLAB is located. And here are a few pictures of the laboratory. The entrance of the laboratory is a clean facility, and basically everything inside is cleaner it's cleanliness. It's basically the level of a facility where they produce the drugs that we receive when we are sick. Basically, that's the same level of cleanliness, because we need to reduce the amount of dust inside of the lab, because the dust is radioactive. It has traces of uranium and thorium, and that if that reaches one of the detectors, basically those radioactive decays, alphas, gammas, and betas, could mimic the signal that we're searching for dark matter. And this is the launch room. This is the area inside of the lab. Here's a hall with some experiments. It's already 2 kilometers below the surface of the Earth. But of course, I think that the best way to give you an idea on how SNOWLAB is through a video. So I'm going to show you a video of the laboratory. Let me play it. Okay, let me go back. I hope that you were able to hear the music because it's very nice. You are very lucky because this is probably going to be banned from YouTube because it has copyright. But I have been playing it in my talks because, as you saw, I am in that video. So I hope that people are able to see it. But basically, I just try to give you a glimpse of what it is to go underground. It's basically descent about 5 minutes at 40 kilometers per hour, and then walk 1.5 kilometers, and then that's the inside of the lab. But I hope that I think Erica talked about this, explain about the snow lab facility. Let me talk about once we are there, how do we reduce the backgrounds even more? So basically, it's everything about backgrounds, backgrounds, and backgrounds. And I'm going to just ask a few questions. So this background, underground and on surface, but underground, that's where our experiment is. It comes from the surroundings, from the detector materials, from the shielding, and even still cosmic rays, secondary reactions and activation. But okay, so these are the questions. So how much radioactivity in becquerel is in our body? What is the most radioactive food that we eat? And how many radon atoms escape per square meter of ground per second? So these are the answers. Basically, in our body, we have roughly 8,000 becquerels from carbon-14 and potassium-40, including 8,000 neutrinos. That's for an 80-kilogram person, more or less. The most radioactive food that we eat, bananas and coffee. Actually, Brazilian nuts, they are 5 times radioactive as these, but in Mexico, they are very expensive. So I'm going to go with what I eat, which is bananas and coffee. And these are the amount of radon atoms that escape from the ground. So as you see, it's a lot of radioactivity. It's not harmful for us. It's basically, we have been living with this. We eat bananas and coffee, and there's no problem with that. But for a wind detector, so this plus the cosmic rays accounts for the 10 to the 11, 10 to the 12 events per ton per year. So we basically need to avoid everything that it is radioactive. That's why we need to shield our detectors. That's why we need to carefully select materials. And of course, we cannot make our detectors out of bananas or coffee, right? Basically, we do a careful selection of the materials. So this is very important. But let me talk a little bit about the experiments. I'm going to skip a few slides that talk about backgrounds. I just wanted to give you an idea of what we need to do. Basically, we need to go underground. We need to reduce everything that it is radioactive. And in addition, discriminate, as I explained, and I'm going to show again. And then we are ready to build and operate our dark matter detector. So the first example that I'm going to show you of a typical dark matter detector, still, this is the leading experiment using argon in the world. And this is called Deep 3600. So this is the experiment. This cannot be achieved by one person. This is a collaboration of roughly 80, a little bit about 80 researchers from Canada, Germany, Italy, Mexico, Russia, Spain, the UK, and USA. Here is 4 years ago when they visit Mexico for the collaboration meeting, and we use argon. And we use argon because argon is a scintillator. Argon scintillates, emits light. So basically, when a wind particle hits one of the argon nucleus, there will be light. So we want to measure that light and know that there was an interaction of that matter. Advantages for using argon, well, we can purify it very easily. There's lots of light. It scintillates many photons. It is very well understood. The temperature to make it liquid is 85 Kelvin. So that's very nice. We can use argon for these experiments. And this is the main background, one of the main background reductions of the experiments. It's called pulse shape discrimination. So as I mentioned, I want to discriminate nuclear recoils from electron recoils. And it happens that the light emitted when we have a nuclear or an electron recoil is different. The light distribution, the light scintillation, it's different, the profile. So we use that. And here on top, you can see a typical example of a an electron recall and below of a nuclear recall. This is a pulse for one of the PMTs that detect the light around emitted when there is an electron recall, and this is when there is a nuclear recall. So if you see, the topology is different. And we calculate a variable called F prompt, which is the fraction of light in this pulse in the beginning compared to the total. And we get some fraction that separates between these two pulses, between the pulse coming from the electron recall and the nuclear recall. And this gives us this band, which is the band of electron recalls, and this band for nuclear recalls. This is the discrimination that I was mentioning, just by the topology of the light emitted by the scintillator, because the nuclear and the electron recall, they are different. In one, the nucleus is recalling, and in the other, the electron is recalling. So we are using that to separate these events. And of course, we expect that dark matter is only produces nuclear recalls. And this is because of the mass that we have where we are searching for dark matter. So this is the detector. It basically consists of an acrylic sphere of roughly 1.7 meters diameter. So it's about this. I think you cannot see it but my hands, but it's 1.7 meters, the diameter. It's surrounded by 255 PMTs, photomultiplier tubes, that are used to detect the scintillation, the light emitted. And then this is immersed in a water tank of roughly 8 meters tall. This is located deep underground at Snow Lab in the laboratory that I showed you. Let me tell you how sophisticated it is to build a dark matter detector. And basically, you need to select pure acrylic. You don't want that your acrylic has radioactive contaminants. So there are very few places in the world where you can buy that acrylic. This was acquired in Thailand. So it was built in Thailand. Then it was shipped to Canada in 4 pieces. These 4 pieces were placed in an oven, and then we got this vessel that I show you in this cartoon, and then it was shipped to Snow Lab, 2 kilometers underground. And then here we put a neck, because the neck couldn't fit through the shaft, basically through the tunnels where it was transported from surface to underground. Then we started assembling it. As you see, there are a few light guides here, which are acrylic pieces that separate the vessel from the PMTs. And this is because the PMTs are one of the most radioactive things in this experiment. So we want to keep them away. Also, they are operated at room temperature, and this is at 85 Kelvin. So there is a temperature gradient. And here we were assembling it with these light guides. Then we couple the PMTs. We place more shielding. This is inside of the water tank. Then, of course, if you are building a very sophisticated detector that costs millions of dollars, so you want the National Geographic to go and take a picture when we were assembling it. And actually, it came in a TV show called Scorpion, where these detectives go underground to solve a crime. And they basically, one of our colleagues saw that they used our detector and our PSD, our pulse shape discrimination, in the TV show. So this is the TV show, and they tried to sketch one of our detector. So it came to the National Geographic, and of course a TV show. But hopefully it will be for dark matter detection, not for only that. Talking about backgrounds, we did many things. We had to polish the vessel to remove contaminants, mostly from radon. We had to calibrate the detector. I'm going to skip a few details, but of course you can ask during the questions. We had to calibrate. We have to understand the response of this detector. And we have done several campaigns of data taking. Since 2016, when we did the first fill, we took data up to last year, when we actually emptied the detector for some fixes. And what we have found? Well, we found 0 candidates. We found no evidence of these dark matter particles. And we did this calculation that I showed you about the rate, and we placed some exclusion curve to rule out properties of dark matter. And this is what you see here in red. This is the best experiment using argon. And here below, you can see experiments that use xenon. I don't work in experiments that use xenon, so I'm not going to talk about these. These have even reached lower cross sections with xenon, and in our case, we are the leading experiment using argon. So this is basically the technology that we use. It's a low background experiment, very sophisticated with clean materials, and we use these techniques to separate nuclear form recoil from electron recoils, and with that, we basically observe 0 events, 0 candidates. So basically, we rule out that dark matter could have this mass range with this cross section. That's the first example that I want to show you in this talk. Since I'm probably 10, 15 minutes, something like that, that's correct, right? I have like 10, 15 minutes. Okay, so let me jump to the other example. So another typical example, but now we search for a different interaction that depends on the spin. So I'm going to skip a few slides. This, I suppose that this will be uploaded at some point. And of course, you can send me emails. I will be happy to answer some of your questions when you review these slides. This is a picture of our detector before the filling of the water tank. Basically, inside this sphere, it is the detector that I showed you. And this is the water tank that it is filled with water. We fill it with water to shield from environmental radiation. The second example that I want to explain is PICO. This experiment is called PICO. It's also a leading experiment, but in this case, with a different coupling and a different material. So we don't know what dark matter is. We don't know how it interacts. So we are searching, or experiments are searching all over the world with different materials, different technologies, and different couplings. Here in PICO, we use bubble chambers. This is the collaboration when they were in Mexico 6 years ago for the collaboration meeting. It's also institutions from Canada, Mexico, US, India, the Czech Republic. And for this, we use bubble chambers. Bubble chambers were used in the 70s in beam experiments, and they were able to detect traces of interactions. This is a picture of a bubble chamber. Now we use it to measure nuclear recoils, to detect nuclear recoils. So instead of a trace, here, a track. So basically, we have single events, single bubbles coming from the nuclear recoils. This is a 5-bubble event produced by a neutron that basically produced nuclear recoils here, 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 and there. So what's the physics behind a bubble chamber? You can make a bubble chamber with any fluid, with any liquid. Here, we are using these fluorocarbonated fluids because they have fluorine, and fluorine has one unpaired proton. So we can search for a different coupling of dark matter, which is through the spin. And it consists, a typical detector consists of a stainless steel vessel, and this is filled with an hydraulic fluid. And then inside we have a quartz jar filled with our fluid, our liquid, in this case, the fluorocarbonated fluid, which is in a superheated state. It is in a superheated state, and then when a particle comes and produces a nuclear recoil, that nuclear recoil deposits energy. I mentioned already a few keV, and that's enough to trigger the phase transition. And that basically evaporates a small amount of material that produces a bubble. And then we have cameras that take pictures of these images, and also acoustic sensors. You probably have seen these physics at some point in your life. Maybe you have heated a cup of water in a microwave, and then you heat it for 2-3 minutes, depending on the power. It is very hot. It's nearly boiling. And then you take it out, and then you take instant coffee, even sugar, and you quickly throw it into the hot water. And you can see how it explodes. If you try this at home, be very careful because it's very, very hot if you haven't tried, or you can search on YouTube videos. That's basically the physics that we are seeing here. It's a superheated state, and then there's a small perturbation that induces the boiling. In our detectors, it's only a nuclear recoil. It's only a bubble nucleation, and we take a picture of that bubble. And once we take the picture of that bubble, we know that a particle crossed our detector, and we quickly have an hydraulic system that compresses and recondenses the fluid. That's basically the idea behind our detectors. And the physics, it's basically a competition between the surface energy and the latent heat. Basically, the bubble trying to boil and the fluid trying to compress it. And one of the interesting features of the detectors is that we are insensitive to electron recoils. And that's because the bubble nucleation depends not only on the energy, but also on the stopping power. So basically, particles, even with high energy, cannot produce a bubble like gammas because they don't deposit the energy in a single place. They do it along a track, and they don't have enough stopping power. Let me show you a few pictures of our detectors. This is one of our detectors. This is the quartz jar with the acoustic sensors, these acoustic sensors. Why do we use acoustic sensors? Well, when the bubble is produced, there is a plink, and the sound that is produced is different for different particles. Alpha particles, which are produced in nuclear decay, in nuclear decays, they are louder than nuclear recoils. So we can discriminate here backgrounds with the sound when the bubbles are produced. Even the bubbles are identical, the noise, the sound is different. So here are a few pictures. You can see here the water tank with the water shielding. This is the shielding, the water used to shield the detector from the environmental radiation. Here is the pressure vessel. Here are a few, you can see the viewports where the cameras are installed, and these red are the LEDs that are used to illuminate the inside of our detector, because we take pictures and we need to illuminate it. So here are a few events of our detectors. Here, there are different detectors that we have built and that we have also used for data taking. In this detector, we haven't seen events neither, as in deep. Actually, no dark matter experiment has observed a convincing signal of dark matter, but we can do the same. We can say what dark matter cannot be, what the cross-section and the mass dark matter doesn't have. And this is basically by excluding these areas. Here are a few experiments, but of course, I'm only focused on PICO. This is the limit that we obtain when we use the first equation that I showed you with the data taken from this detector and all our data analysis. So since I would like to have some questions during my talk, I'm going to skip a few other studies that we did for other properties of dark matter. We don't know how dark matter interacts. We don't know what it is. That's why we're searching it in different mass ranges and different interactions. And I show you spin dependent, spin independent, but there are other models, theories that we can test. And we haven't observed it, but that's very valuable because we can exclude properties of dark matter. And of course, we expect that at some point we will see dark matter if it is one of these WIN candidates. But of course, there is a community all over the world using experiments with different components, xenon, silicon, germanium, all of them building detectors, low background, deep underground, to search for these tiny signals. And nobody has observed it. Nobody has observed a definite signal from these candidates. So this is very exciting to get to work on the ground. I'm just flashing some pictures of our detectors. This is the detector that we are building and we are commissioning and about to start data taking this fall. Here you can see the detector. This is the quartz jar. Here it goes the fluorocarbonated fluid. And this goes inside of this pressure vessel and then inside of this water tank. The idea is to keep our detectors very quiet, radioactively speaking, with the lowest backgrounds in the world. These are the cleanest places in the world, basically, with really tiny amounts of impurities, radioactive impurities. This is a picture of our detectors from 3 years ago. No, this is actually from 5 years ago. So when we deployed our inner vessel, our quartz jar inside the pressure vessel, then we fill it, we close it, we fill them with water, and then we wait. We wait for 1 year, 2 years, hoping to see one of these signals. Nobody has observed a definite signal of dark matter, but it is very exciting to develop all this physics and to achieve what, or to say what dark matter cannot be. So I'm gonna skip the last detector. Of course, I'm gonna write my email in the chat, and it can be shared with you if you're interested in some of these detectors of these collaborations that are all over the world in these deep underground facilities. I'm gonna finish with these two. Basically, here you have some scientists arguing that do you think it's a neutralino? It could be an axion, or it could be an S neutrino from different theories. And from other guys, it looks like a bit of a spin, right? We don't know. We don't know what dark matter is. We don't know what the properties are, but we are searching over different mass ranges and with different couplings to try to find it. We don't know what the dark sector could be. We know that there is something missing in the universe, that there is 95% of the universe that we don't know. And of course, there could be amazing things behind this in this dark sector. So I think that that's it. I overestimated my capacity to deliver slides. So I have many more slides, but please feel free to ask.
Yeah, well, thank you, Dr. Eric Vázquez. There are some questions in the chat and from YouTube, so let's start reading those. So Cesar Martinez Cruz says, thanks for your amazing talk. Do you think there are different types of dark matter, dark energy, or there is only a single kind?
So more than I think, well, yeah, it is, I think, or I believe, I guess, we still don't know, right? There is no evidence. But just by comparing with our standard model, it would be weird that this dark sector, it consists of only one particle, right? So it could be very rich. That's what I think. At least two, maybe more for dark matter. Dark energy is another problem. We don't know if a particle could solve it. Actually, it probably will not solve it. So there is something different there with this accelerated expansion of the universe. But for dark matter, I think that this dark sector could be very rich. Basically, the reason why is we are used to the energy mass ranges of the standard model, right? Up to a few TeV. So there are still higher energies, and we don't know how rich could be another sector, in this case, the dark sector. So that's very exciting. There are many theories. We don't know, but of course, we are doing experiments to test it.
Thank you. There is another question by Evgenija. So it says, how does it feel to be that far underground? Doesn't it get a bit scary, or does it just take time to get used to?
Yeah, that's a very nice question. Well, in the beginning, it feels I don't know if it's scary. Yeah, I think that for some people, it's scary. It just feels weird. I mean, the pressure of the atmospheric pressure increases 25%. So, and that goes in 5 minutes. It is not when you are flying, right? That the plane takes about 1 hour or whatever to descend. This is 2 kilometers just in 5 minutes. So that actually, it's very interesting. When you have a cold, I mean, you can just pass out there just with the increase in the pressure, because you cannot balance the inner and outer pressure. So, but independently of that, pessimistic scenario when you are sick, at some point you get used to, right? You get used to, it's like another day in the office. I did that for 6 years, and you only get really tired working underground. You work 10 hours underground. It's very well known, it's safe because the majority of these laboratories are in dedicated places. For example, Snow Lab is in an operating nickel mine. So we descend with the miners and the physicists, right? Of course, you can distinguish because the miners are very strong and very tall, and the physicists are a little bit not that tall and not that strong, I would say. But it is very exciting to do that. You get used to that. It's an amazing experience.
Yeah, cool. I actually have a funny story about it. I will just share it like really quick. When I was in Canada, we had the chance to go to Snow Lab. So because of a conference, right? So after we went down and we visited all the labs and all the stuff, well, we went back to ground, right? And the following 5 days, I was like super dizzy, like having like vertigo and all that stuff. And when I went back to Montreal to visit my doctor, because I was like super dizzy after going down, he mentioned that some crystals we have, I think there are like calcium crystals in our ear, like inside our ear. So those crystals were just like moving around, and my vestibular system was like going crazy. And I think it was related to when we went down, like the pressure might have popped my ear or something like that. And it was like crazy. So I had to share my experience with the organizers of the conference, because it was like crazy. And I actually asked if someone else has had the same issue that happened to you at some point.
No. I mean, yeah, I can understand that change of pressure. It didn't happen to me. It's not that happens very often, right? Those type of incidents, but it is a different environment, right? So yeah, I can see that.
Yeah, well, everything for science.
Yes. Underground, I mean, it's complicated to work there. And at Snow Lab, there are not only experiments on neutrino physics and dark matter searches. There are also people doing experiments where they take fruit flies underground and see how they behave with the change of pressure, just to study that effect in humans, of course. But of course, they do the test with the fruit flies. So there are lots of exciting science, I would say, because this is biology. Underground, right?
Yep. So we have just time for these two last questions. So Santiago Alvarado Orozco says, thanks for the very interesting conference. I'm not sure if it's a very basic question, but how are we sure that we are not eliminating the YMPs with all the elimination of background radiation, or we are just hoping we are not blocking them?
Okay, no, we cannot. Basically, what we are eliminating is the environmental background radiation, the one that we know. We cannot eliminate the WIMPs because their cross section is very, very, very low, so small. So basically, the Earth doesn't block them. Our detectors doesn't block them, because of the tiny cross sections. So there is no way that we are by eliminating the background radiation that we can get rid of the WIMPs. What we could do is that we are searching in the wrong place. So all the plots that I showed you go from 1 GeV to 10 TeV, more or less. So what if the mass of the dark matter particle is outside that range? That could be. Of course, we are searching in the wrong place. But as I said, we don't know what it is. So we are searching everywhere, and we are excluding possibilities.
Okay, and our last question is from Enrique Iñiguez. Thank you for such an amazing conference. My question is, if there were different types of antimatter, would it be possible to differentiate them with these experiments, or would they all have the same trace?
Yeah, dark matter. Yeah.
Dark matter, yeah.
Enrique just clarified. Yeah, I understood dark matter. Yeah. I didn't use the word antimatter in all my talk up to now, right? So yes, dark matter. There is one possibility. If they are different in mass, let's say that we're immersed in this dark matter halo with one of 1 GeV and another one of 10 TeV. So they will leave different energy recoiling spectra in our detector. So we would be able to differentiate this with our experiments. The trace would be different. Well, not the trace, the energy recoil spectrum that we will measure will be different, and we will know that there are two components, for example. But there is one. This is assuming that those two, for example, I'm just using as an example too. If these two are in the ground state, and those are the ones that we observe, right? But because it could be that one of these dark matter particles, state 1, is the ground state, and state 2 is an excited state. And basically, in the current universe, there is only ground state, dark matter 1, I'm going to call it. So there is no way that we will see dark matter 2, state 2, an excited state, unless we excite to that state, which also could be possible with these experiments. And that would give you a different energy recoil spectrum. So in principle, if there are sufficient different, we should be able to differentiate them with the energy profile, we could say, the spectra, right? The energy spectra that they will produce in our detectors.
Okay, thank you for your answers. We are a little bit over time, but I think if you want to ask any more questions, you can let me know, and I can share your questions to Dr. Eric Vázquez. So now I would like to make an announcement. So we are moving to Gather Town since the poster session has just started. So please join us in Gather Town. Remember that you, at the end of the conference, you will vote for the best poster, and the best poster will get a top prize. So make sure you go and visit all the posters and vote as well. Once again, thank you, Dr. Eric Vázquez, for accepting our invitation and to be here at ICPS 2022.
Thank you. I hope you enjoyed the talk.
Thank you. See you.
Okay, bye.